My teammate sounds like a duck.
Sally, you can put it in your pocket.
There's just stuff like that in the water. No, that's it. That's the bottom. Then we turn it upside down. Don't split it. They don't turn it upside down. They don't. No, they don't. Keep them right. Da da da.
Yes, like that.
Da da da. Da da da. Da da da.
Ronan.
Nico. Da da da. I don't know how she does it. The water disappeared. That one. Da da da. What happened? It evaporated.
It can't evaporate that fast.
No.
It did.
She put glue into it. I love
That's the same trick. What did you pour in that? Baby powder.
baby powder. Baby powder.
Baby powder.
Homemade baby powder. And then
All right, can we get another round of applause for Jamie? All right. So what Jamie just demonstrated was a unique property of sodium polyacrylate, which is used in diapers and absorbs an incredible amount of water. What's really cool about that stuff is if you take it and it's already in the gel form, it's absorbed the water. If you add a salt to it, the salt will suck the water out of the gel, and it'll turn back into the powder that you saw her pour on. Even more neat is, think about what that means with your diaper and a baby, right? Because urine has a lot of salts in it, which means they actually can't just use straight polyacrylate gel. They have to add more things to it so that it eliminates that property. Now, we're going to go over a number of reactions tonight. All of them involve change. Now, you know how you take your Legos and you can build things with the Legos, and you take it apart and then you build something else with the Legos? Well, that's all that chemists do. They take molecules, which are made up of atoms, they recombine them in different ways, they take them apart, and they build them back up into different forms. And so we're going to largely be doing that today, along with a few phase changes, where you go from one type of matter into another, from a solid to a gas, for instance. But first we're going to start out by trying to put out a candle with gas. Okay? Now, standard
A visible gas.
tea light. And what do you think is going to happen if we take this cup and pour it out over the light? What do you think is going to happen? Think it's going to go out?
Nope.
Think it's going to go whoosh?
Gas. No, I think it's gonna go. It's gas.
No, it's not gas.
Nope. It's going to stay put. Now,
The next
that's because what gas is in here?
Air.
Air, that's right. But what if we actually add a different gas? What if we add a gas that will take away the oxygen and start the flame? So, Kara, would you like to?
Sure, so what we have here is some baking soda, which is sodium bicarbonate, and some vinegar, which is acetic acid. Have you guys all dealt with this stuff at home, maybe baking cookies or something? Yeah? Okay.
I know.
So what we want to do is just mix these two things together to form a reaction that makes carbon dioxide, and then we're going to try to pour it into our cup, which is over here, our empty cup, and then try to put out this light.
Same
Okay,
empty cup.
so again, same empty cup, nothing happens when you pour it on. So what I'm going to do, also watch carefully because we're going to ask for 4 volunteers or 5 volunteers after this to do the experiment. So watch us do it first and then you guys can do it yourselves. Okay, so on the count of 3, I'm going to pour it in. Ready? 1, 2, 3. So there are some bubbles. What do you guys think are in those bubbles?
Gas.
Gas? What kind of gas do you think it might be?
Carbon dioxide.
Carbon dioxide? Possibly. Okay, so these bubbles are now popping and the gas is sticking into the bottom of the cup because it's heavier than air. So I'm just going to pretend to pour the water, but I'm actually pouring the gas. So it looks like a pretend tea party. Front row, is there any water in here?
No.
Okay. So now I'm going to try to put out the candle.
That was gas.
Good.
Can we get 5 on? Okay.
Did you guys try pouring the empty cup on the glass on the bubble?
Okay, that should be good. And then, what do you think is going to happen?
Pour the
Oh,
gas
here,
in,
use this
dip
one.
into the water. You might want to pour a little bit more of the gas.
Yep, do it quick. Whoa!
The gas is
Five for 5 there. Good job. All right, excellent job, everybody. That was a volunteer. So we just used a solid and liquid, combined them to form a gas, and then used that gas to put out a fire. Pretty cool. Now, I don't know. Are you getting hot in here, Kara?
Ooh, it's pretty hot in here. I could really use some water.
Yeah, me too.
I have some water right here.
Okay, well let me get us some glasses.
Oh, that looks awesome.
But you know, we only have water, don't we? Because I could really go for some juice
Ooh,
too.
juice sounds really good right now.
All right.
Well, here's some water.
Oh, thank you very much. Oh, fantastic. Oh, we're running out of water.
Yep.
All right. Now, okay, I'm going to ask my magic cup to give me some like grapefruit juice.
Ooh, grapefruit juice. I'm going to ask for some strawberry juice.
Ah, okay, that sounds good to me. Okay, do you guys think that we can get water and turn it into juice?
Yeah.
You think? Okay, on the count of 3. 1, 2, 3. Wow.
That looks like some really good strawberry juice, and that looks like some really great grapefruit.
Okay, would you like a
Oh,
straw?
that's always
I always
drink
take my juice with a straw. All right.
This is good. Dr. Matt, are you blowing into your juice again? I know, like, at least my mom told me not to do that when I was younger because the Magic Cup doesn't like that and it gets everywhere. And I think the Magic Cup is going to make it turn into water.
It is.
Look at that! Wow! That was so
What? Why would you do that to me? I want a juice. Okay. Well, actually, what we did here, do you think the glass is really magic?
we knew we couldn't trick you guys.
Yeah. Oh, we got to back up
Oh
on the
yeah,
line,
blue
though,
line,
please.
guys. Blue line.
So what we've done here is we've used a pH indicator called phenolphthalein, which in the presence of a base turns a different color. In this case, this kind of light violet. And what's neat about an indicator is that means if the pH is above a certain threshold, it'll be that color, and if it's not, then it'll slowly, the color will get lighter and lighter until it's clear. So for instance, we can take the cup, which is now clear, and it's clear because when you blow water or blow air into the liquid, you're actually making it, you're removing the basicity, turning it back into neutral. And we can make it basic simply by adding another base and turn it back into juice. Yes?
Is it actually drinkable?
I wouldn't. The base isn't going to hurt you. The phenolphthalein is in such low concentrations it probably won't either, but I wouldn't recommend it.
I think regular juice would probably
Regular
taste better.
juice is going to taste a lot better. But yeah, so we turned water to juice and then back into water through the use of a pH indicator, which is kind of cool. Now, who here would like to see some liquid nitrogen next? All right, so shall we set the mood then? All right, now liquid nitrogen is extremely cold, and nitrogen is in the atmosphere all around us all the time. But what they do at an industrial scale is they take air and they separate it into its component gases, which are then liquefied. And liquid nitrogen is extremely cold, okay? So I need everybody to stay behind the blue line. That's just added on top of a little bit of water. It's just boiling off.
So, who thinks that they can break a penny? Does anyone think they can break this penny? You want to try?
Yeah.
All right, pass it around. Everyone try to break it. Pretty hard, huh?
It's really hard.
Pretty hard. All right, so the front row is still trying to break the penny.
Back up, back up.
Yeah, make sure you stay behind the blue line.
Okay. Now, has anybody been able to actually break the penny?
No.
No?
Not successful.
Okay, now we've just taken some standard pennies and we have them in the liquid nitrogen between shows. Now, do you think Caro will be able to break the penny?
Yes. I hope he will. Hammer, yeah.
Well, we could try a hammer on the other ones
Yeah, do
too.
you want to try it on the other one first?
No. Yes.
All right.
Yeah.
Let's try this one. Does not break. Let's see if this one does. Broken penny!
Dad, maybe those lady
Maybe it was just that penny. Should we try another
I
one?
think we should try another one.
No, I
because
think we
science
shouldn't.
replicate.
I think we shouldn't.
Broken penny again!
That would just make sense. That's what we're doing.
All right. He does the experiment. Okay, now standard balloon. I'm going to feed it here to the liquid nitrogen that we have in this vat.
This vat hasn't eaten in days, so it's really hungry for
Maybe we
balloons.
should get another one too.
Oh, yeah.
Sit down,
Maybe
bug.
one of these
Sit
animals.
down, bug.
Sit down.
Sit down, bug.
One of these.
Sit.
All right, now one of the neat things here, when I pull this out, look carefully. At the bottom, you're going to see a liquid. That's actually liquefied air. so cold it liquefied the air, separated it out, and then of course it heats up. I think it forms a little. Behind the blue line, behind the All right. So for the last experiment, let's say you're out. Okay, let's say that you're out with your elephant family friends, and boom, it's nighttime, and they have to brush their teeth, but they forgot their toothpaste.
I love this.
And so, what do you say? Should we try to make some toothpaste for our elephant friends?
Yeah.
All right. So let's start with the baby, shall we? Let's make some. Oh, and actually, I realized we have. Yeah, we're gonna skip the baby. We're gonna go to the adults.
Yeah.
As for a lack of preparation. All right. So let's make some elephant toothpaste for the adults, shall we? This is a kind of cool reaction. What we're doing here is we're going to take concentrated hydrogen peroxide and we're going to convert it into oxygen gas. And we're going to trap the oxygen gas in a series of bubbles, okay, which is caught by detergent. And it forms of what's called a very exothermic reaction, which means it gives off heat. So we're going to start with about 100 milliliters of concentrated hydrogen peroxide. We're good.
Okay. And what color should we make their toothpaste? We have red,
Yellow.
red,
Red.
Okay.
Blue. Red and blue. Can you mix red and blue?
Purple.
Add some blue to it. Red and yellow. Red, blue, and yellow. Red and yellow or blue?
Yeah, blue
Okay,
stripes.
we're gonna try for blue stripes.
Last show of the evening. Gotta really hit the bling.
Can we do yellow?
Clean it up.
All right. That's enough.
Okay, add a little bit of detergent. Stir it up. And here, you want to do the honors?
Sure. Gotta put on my safety glasses. Okay. Okay, can I get a countdown from 3?
2, 1.
Oh my.
Oh.
Do you think that's enough toothpaste for the mother elephant?
Okay, now this hasn't worked in the previous experiments, but let's try again. Okay, so we're going to take this this match, blow it out, stick it in here, and hopefully. Well, yeah, it's hard to see. It's hard to see. So it actually, there's enough oxygen in the foam after we let it go that it will catch the light. It'll turn the embers in the match back into a flame, and so you can pull it out and the flame's back on. But it's awfully hard to see. So we'll skip that part. But
Awesome.
yeah, last show of the evening. I hope you guys had a good time. Learned something.